Hi, Taxiland people. Today we're going to be looking at differentiation, stationary points, and directional derivatives with some multivariable calculus and other things relating to AI and how we can apply it to things like gradient descent. So let's jump right in. So, firstly, I'm sure all of you have had experience with differentiation before. You may have done it at further maths at GCSE, and you would have definitely done it for A level maths. So, differentiation in essence just allows us to find the rate of change of one variable with respect to change in another variable. And if we're finding the change in y with respect to x, we say dy dx, meaning for whatever change we have in y, I mean x, how much change do we have in y corresponding to that? Sorry. And the way we write it down or the way we differentiate can be represented in this simple step written at the top. F of x is equal to kx to the n, where x is the variable, the others are constants. The derivative of that would be kn x to the n minus 1. So we multiply the exponent to the coefficient, and then we decrease the exponent by 1. Other terms you should be familiar with before we continue is the term monomial, which is just an expression with one term, and more importantly, polynomial, which is an expression with multiple terms. Right, let's move on. I'm sure everyone's happy with differentiation. It was an A-level recap. So just wanted to have a quick look at this question. 2x cubed plus 3x plus 9. Can we differentiate that with respect to x? So just type your answer into the chat, and yeah, it should be just fairly straightforward A-level recap. Yep, 6x squared plus 3 is correct. Good job, guys. I can see everyone typing that in now. Great. Let's get moving. So, trig and natural log. These are basically still part of A level and just slightly more unconventional and different functions that the first simple rule I gave you at the start would not cover. So this includes trig functions. You need to know that sine differentiates to cos and cos differentiates to minus sine. The exponential, so that's e to the x differentiates to itself. In fact, that's the whole point e exists. It's because it is an exponential that differentiates to itself. And finally, the natural logarithm, which can otherwise be defined as log e, that differentiates to 1 over x. We can go through proofs of this, but they are not required in our exams, so I'm going to just assume this knowledge without proving it. So I hope that's fine with everyone. Let's have a look at this first question then. So f of x is equal to x squared plus e to the x plus 2. Can anyone tell me what the derivative of this function will be? Just type into the chat, and I will keep an eye on the chat now to stay tuned to your answers. So let's see.
Right. Okay. Yeah. Yep. Okay, cool. Yep. You seem to be getting it. Next question. Yep. That is correct. And final question. Ooh. Mm-hmm. Right. People are saying 1 over x plus 3 will go. All right. Next rules that we had was a chain product and quotient rules. Um, you should also be familiar with these rules from A level. So basically, yeah, these are the rules. I'm just going to give up some questions here. So x e to the x. So x is obviously the variable. So yep, you have to use a specific one of these rules to solve the yeah, to differentiate it. So does anyone want to have a go at it? So yeah, just put your answer in the chat. You were saying x e to the x plus e to the x. That is correct. Good job. Now here's a real sticky one, right? Try this one. This one employs many different rules. And I'll give you some time with this. It should take a little bit of time. Don't worry about simplifying once you have the answer. I just want it in the form of like exactly how the rule dictates it. You don't have to simplify it. But I can understand it might be a bit of a challenge doing it in latex. So if you want, just do it in like with pen and paper and just send a picture on the chat or like a screenshot if you have a drawing tablet or something. How are you guys getting on? We getting on with this question? Anyone got any answers yet? Let me in the chat. Let me know in the chat how you guys are getting on with this. Good. 7. 7? What? I hope that turns into times the derivative of is ln x e to the x minus 1 ln x squared. Yeah, so you have the for plus cos. Okay. Yeah. Okay, so you just wrote it out as a derivative. So it should be ln x e to the x cos x plus e to the x sine x minus e to the x sine x over x, and then all of that is over ln x squared. Would you like me to send you a picture of this? It might be hard to visualize what I'm saying without, you know what, I'll try and send a picture. Let's go to chat. All right, I'm doing it on my phone. Camera. All right. That's what I had in my rough work there. So du dx was just the part, like the half derivative. Ooh, need to disconnect from here. Right. Hello? Can you guys... Did I leave? What? I'm still here. What's going on? Oh. Okay, I feel like I might have gone off the stage real quick, but I didn't say anything, so... But can you guys see the picture? Do you guys understand how I got to that? Yep. Okay, cool. Great. So yeah, it was just a case of using the quotient rule along with the trig values we learnt earlier. Finally, I think I have one more question here. Yep. So this one should be easier than the last one. This one's a case of using the chain rule. Can you guys tell me what the answer to the derivative of sine e to the x is? Okay, right. Yeah. Luckily, the screen is actually getting recorded, even if it's not being shared, so that's fine. So look at the recording as well later if you want. But yeah, so can you tell me what is the derivative of sine e to the x? Cos e to the x times e to the x. Yep, that's absolutely correct. Good job, guys. So that's the chain rule, the product rule, and the quotient rule. Next. Yeah, a lot of stuff to take in on this slide here. So if you want like screenshots, the recording will be out anyway. But in all honesty, it is just again A level stuff that we recapped in AI first week. So just stationary point is any point on the graph where the derivative is zero, so it's just a plateau or a flat part of the graph, and we can use it by solving the equation for x in the derivative of x equals zero. And the reason why this is significant is because it can tell us that about the location of peaks, aka local maximums, or troughs, aka local minima, off the graph. So a graph can have multiple stationary points, but the highest maxima and the lowest minima are called the global maxima or minima. Um, and all the other ones that aren't the global one are called the local maxima. Any point that goes up and starts going down will be called the local maxima. Any point that's going down and starts going up will be called the local minima. And then there is the second derivative, which I'm sure everyone's covered at A level as well, is you can substitute in the value of the stationary point that you got by setting the first derivative to zero. So you have a coordinate for x. And then you work out the second derivative, which is basically you differentiate the first derivative again. And then you say you can work out what the nature of the stationary point is. And by nature of the stationary point, it means like, is it a maxima or a minima? So if the second derivative is greater than zero for the point that you've worked out as the stationary point, that means it's a local minimum. If it's less than zero, it means it's a local maximum. The other case, obviously, the second derivative could be equal to zero exactly, and that would mean it could be a point of inflection, but you can't inherently say that just because the second derivative is zero means it's a point of inflection. All points of inflection have second derivatives of zero, but not necessarily all second derivative equaling zero mean like is a point of inflection. So it only works one way around. What else could it be? It could be I can't. How do I draw this out? It could be like a function that's not a point of inflection. A point of inflection uh, is separate from just the second derivative equals zero. So yeah, a plateau, for example, a point of inflection would mean a stationary point, right? However, sorry, no, a second derivative. We worked out a stationary point, yeah, but not all points of inflections have to be at a stationary point or including a stationary point, because stationary point is just with the first derivative, whereas point of inflection is more with the second derivative. So um, yeah, it doesn't need to be a point of inflection. However, if it is a point of inflection, then you can guarantee that the second derivative of that is zero, but not the other way around. If that makes sense, cool. Yeah, makes sense, cool. All right. Monotonic function, and text block on the right, is basically a function that preserves the direction it's moving through all the values of the independent variable. For example, if we had a function such as, I don't know, y equals x, that's monotonic because it's constantly increasing, aka it's an increasing function. If the gradient is always positive or always negative, that means it's a monotonic function, aka it's always moving in the positive or negative direction, and it has no stationary points. So that's what a monotonic function is. Cool. Let's move on. So here's a question on stationary points real quick. So locate the stationary point on the graph 2x squared plus 5x plus 2. So and then we're going to work out what the nature of the stationary point is. So first, can people tell me what the coordinates of this stationary point is? Three messages. Hold on. Anyone? Just just a differentiation. X equals 5 over 4. Um, right? Is it 5? Oh, minus 5 over 4. Yeah, cool. That is correct. That's the value of X. But coordinates rely on us having 2 points, right? So what's the Y coordinate? It is negative 5 over 4, by the way. Um, that's fine. Don't worry. So what's the Y coordinate then? Y coordinate. Okay. Minus 9 over 8. Good job, Victor and Sid and yeah, everyone else. Cool. So that is the coordinates of the stationary point, meaning this quadratic curve has a stationary point at minus 5 over 4 minus 9 over 8. However, right now, we don't know whether this point is a minimum or a maximum. Well, it's a quadratic that has a positive coefficient of x squared, therefore we can tell it's going to be a minimum point. But suppose we didn't know that, how would we work out the nature of this stationary point? How can we tell that if it's a minimum or a maximum? Can you tell me just the value of the second derivative that you'd get, since we kind of know um, that it's going to be a minimum point as it's a positive x squared coefficient quadratic? 4, exactly, cool. So therefore that's greater than 0, therefore it's going to be a minimum point. Cool. So it seems like we're good with stationary points. Now here we take things beyond A levels. So this is now where it starts getting interesting. Multivariable functions, and how can we perform calculus on multivariable functions? So there are two ways to differentiate a function if it has multiple variables: implicit differentiation, which is what we learned at A level, and partial differentiation. Unfortunately, we only need to know about partial differentiation, so you can chuck your like A level knowledge out of the window with that, with implicit differentiation. Um, Partial differentiation is when you take a partial derivative of a function with respect to one variable and you treat all the other variables as if they were constants. So you only look at one variable, everything else is a constant. And then this allows us to mathematically model how the whole function changes when we change a single variable while keeping others constant. AKA, we can basically measure the effect of one variable on the function and what effect does it have on the function if we just change that singular variable, which can help us with a lot of processes like optimization and gradient descent, etc. Um, so commonly, it makes sense to do this in 3D space because we want in 2D space, we only have X and Y as the variables to work with, so it doesn't really make much sense. But the examples in, well, the next couple examples will be in 2D space simply because they're and easier to work with and they're quicker. And then you can just reproduce it for 3D space by just doing the same thing with more variables. So 3D space is common for partial differentiation. And there is a key term that you need to know for our exam, and that is the directional derivative. And what this is it's a function in a given direction at a given point. and is the rate at which the function changes in that direction at that point. And that's a terribly worded thing, but I felt like that kind of encompasses the entire definition. So if you have a function, say, the typical gradient descent concave kind of shape in 3D space, what a directional derivative would tell us is what is the gradient at a certain point in the direction we want to go in. So say if you want to go like, I don't know, but I'm gonna say left. It's completely like unbased and unscientific to say left. But say if I'm at a point on the gradient descent concave curve, and I want to go left. So the point that I'm at is where we're gonna start, and the direction I've given is left. So what this is gonna output, the directional derivative, is what is the gradient of the curve if I want to start moving left. So when we're at a point, specifically in the application of gradient descent, from a point, it'll work out the directional derivatives of a bunch of directions around that point, and then proceed to take the direction with the steepest downward gradient and move the point that we're working the direction out for to that new point by the learning rate, which is represented by alpha. So, but more on that tomorrow. That's more supervised learning. I'll be doing a session on that tomorrow, so stay tuned. So, how do we actually do it in practice? So, this is the notation. This is actually a screenshot from our first lecturer. And it was in week one where we did this, and it says the partial derivative with respect to x is the ordinary derivative, and the function of x being treating the other variables as constant. So what this basically means is we just assume x is the only variable. That's like we're differentiating and x is the only ordinary variable, and everything else is a constant, as I mentioned earlier. What's more important here, I think, is to look at the notation. So partial differentiation is not the typical dx or dy dx df dx. It's actually this weird squiggly symbol, which I'm not quite sure what it's actually called. If you know what this symbol is called, some kind of Greek alphabet, put it in the chat. But yeah, it's this weird squiggly symbol, f, and then that, I think I'll just call it a d for now. So it's called lowercase delta. That's okay. We'll call it delta. Cool. Yep. All right. So delta f delta x would give us the partial derivative of the function when we're treating x as the only variable. Everything else apart from x would be the constant. And delta f delta y would be when we're partially differentiating with respect to y. So we treat y as the only variable, every other variable would be the constant. So it's always you partially differentiate f with respect to one of the independent variables in f. Hence why it's always delta f over whichever variable you are differentiating with respect to. Kind of like dy dx with when we did normal differentiation. Right, so I have a question here about involving partial differentiation, and this is the question we're going to carry on for a large remaining part of the session. So will the question come up? Okay, cool. This is the question. I'm going to give you some time to solve this. And then I want to be able to invite someone onto the stage to explain to me what they did and their process. If you want to just do it on stage right now, please just tell me in the chat and request to come onto the stage, and I'll add you onto the stage. If you want to do it first in your own paper, which I perfectly understand, and then come up on the stage, that's also fine. But yeah, what are the partial derivatives of this function? So basically, I'm asking two questions here. Can you find me the partial derivative with respect to x and then with respect to y? So two separate answers, part A, part B, kind of. Yeah, that is correct. Yep. Uh, are you gonna type onto the chat what you did, or like does everyone understand how to do it? Because I understand this is content that we didn't do at A level, so if there is some confusion, please let me know. Um, do we need Shay to come up and explain, or are we good? Put in the chat if you want Shay to come up and explain, or if you guys get it. Okay, Victor's saying he gets it. Cool, cool. We get it. We get it. All right, Shay. All right, I see what you get it. But he should still get onto the stage. I kind of agree. Well, but yeah, I agree with other Fred. I think people want you on stage, Shay. I feel you must be invited to speak and explain your reasoning.
I'm getting cyberbullied. To find the partial derivative
Mm-hmm.
for x, you just imagine, like you said, y is a constant. So x squared y would just become, we look at the x part, y is like a constant coefficient of x squared. So it just becomes 2xy. We just keep that y. And then in the same way, 3y squared in terms of x, if we try and differentiate that, we just get 0. And then the same for y, but we treat x squared as a constant.
Mm-hmm.
Yeah.
Okay. Yep. I agree with your reasoning. That's what I would have done. In fact, that's the only
Clearly, yeah.
thing you can do. Thank you for getting onto the stage, Shay. Can we get some applause in the chat for Shay's bravery there? All right. Cool. So this was the answer there. So as Shay said, we treat the other variables as constants, and so the derivative with respect to x, as denoted by delta f delta x, is just 2xy, and then the partial derivative of with respect to y is x squared plus 9y squared. So I did actually have the reasoning just here on the next slide right here, but it was fun to get Shay to come up and explain it anyway, right? So that's all good. So the gradient of fxy is 2xy x squared plus 9y squared, right? So this is an important piece of information. The gradient is what we're going to call 2xy, and the y coordinate being x squared plus 9y squared. So this is what we decide as the gradient, because we have two different gradients here. All right. Now we come on to, so we just did partial differentiation. I hope everyone understood that. How could you not with Shay's lovely explanation? And then how can we use that? And the answer is with directional derivatives. By the way, I know in the calendar event it said differentiation, directional derivatives, and gradient vectors. I'm not too sure why that was the case, because a directional derivative is in fact a gradient vector. They are one and the same thing. They mean the same thing. This basically tell us that the gradient in a certain direction at a certain point, which is useful for application like gradient descent. And I explained this before, because you want to always traverse the steepest negative gradient. So you want to find out the gradient in every direction around a point. Okay, so we're now actually going to look at the question that we just did. And we're going to work out the directional derivative at point 1, 1 in the direction vector 1, 1. So I used 1, 1 because it's very, I'm just trying to show how it works, and it's nice, easy numbers to work with. But suppose we're on a 2D space, and we are at point 1, 1, and we want to find out what is the gradient if you want to move in the direction 1, 1 of our previous function, which was this one here, x squared y plus 3y cubed. So that function, we are now going to work out the directional derivative in direction 1, 1 at point 1, 1. So can you guys have a go at this, or would you like me to like kind of I'll go into this and I'll be revealing the next bits like that, but I want you guys to have a go at this first. Can you calculate the directional derivative, or aka the gradient vector, for this
at
0.11 and direction 11. Or can anyone tell me what the first step would be on the chat? Or, I mean, if anyone really wants to speak and go through the entire thing as well, I'd be happy to have them on stage. All right, let's take a look at the chat. Other Fred says monkey gif. Nice. Never odd or even says, do you sub in 1 for x and y? Exactly, yes. So we calculate the gradient function as 2xy x squared plus 9y squared, as Shay explained before. So basically, as Never or even said, the gradients at 0.11 is then given by the substitution, or we sub in 1. 2 times 1 times 1 is just 2, and then we have 1 plus 9, which gives us 10. So 210 is now the vector we're working with for the gradients at this point. Any gradient at this point, we'll be working with 210. What do we do next? So we've done it with the point, but this is irrelevant. Like, this information doesn't mean anything. Like, it's insignificant. So we can only use this information now if we have a certain direction to go in. So the direction I gave was direction 11 as well. So what is the next step we do then to be able to use that direction? Monkey? Who are you calling a monkey, Victor? Oh, right. That's you're calling the other Fred. Yeah, facts. Okay. Yeah, no, don't worry. I get it. Why? So wolf? I had never seen a wolf like that. Okay, cool. Stay on task, guys. Um, anyone know what the next step is? Standardize the direction into a unit vector. Oi, Shay, in here again. Yeah, that's correct. So we can only use unit vectors, aka where the vector's magnitude is equal to 1. So for the vector 1, 1, we actually need to standardize that into a unit vector, which is what we have to do. We have to make the magnitude equal to 1, right? Because we only want to work with the direction. We don't want to multiply it by the magnitude because that would skew our results. So to make the magnitude 1, we just work out the magnitude. So the magnitude of the direction vector 1, 1 is root 2. That's just by Pythagoras we're using to work that out. And then we can say that v hat, aka v as a unit vector, is then 1 over root 2, 1 over root 2. We're just dividing the x vector and the y vector, or the I and the j vectors, by root 2 each, and that will give us now a magnitude of 1 if we were to work out the magnitude of this vector. Right, okay, so now we have a gradient at the point, and we also have a vector that we want to work out what the gradient is in that direction. So what is the final step that we need to do to calculate the directional derivative? Anyone? Are we not too confident with directional derivatives right now? No? Okay, that's fine. So the last step to calculate the directional derivative, sub in the unit vector j into x and y. Not quite. We already used this and subbed in 1 and 1 and got 210 out of it. So we have this, which is what we would need to use to calculate any direction from the point 1, 1. So this is a standard result at 0.11, and we have to use this to calculate any direction from 1, 1. So we're talking about this direction 1, 1 in particular. What we'd have to do is, as Sid said correctly, we dot product the unit vector with the gradient vector. So here we have it, guys. We dot product the gradient with the direction we want it in. So we dot product 210 with 1 over root 2, 1 over root 2. And that gives us, 2 multiplied by 1 over root 2 gives us 2 over root 2, and then 10 multiplied by 1 over root 2 gives us 10 over root 2. We add these together as we do with the dot product, and we get 12 over root 2, which I've rationalized and simplified to 6 root 2. 6 root 2 is our final answer, and this is the gradient vector of x squared y plus 3y cubed at point 1, 1 in the direction 1, 1. And that would be what you need to say in your final answer, or that is what we've worked out, kind of. So if we were a gradient descent algorithm, just put yourself into the mind of a gradient descent algorithm right now. We've reached point 1, 1, and we're looking to go in direction 1, 1. We now know that if we go in direction 1, 1, we're going to actually go up 6 root 2. So we definitely do not want to go in that direction because we want to be going down, right? So, yeah, that is the gradient vector, aka directional derivative. Okay, now to end off, that you may have noticed that this was a question in 2D, so it doesn't really make sense to visualize this because it's a lot easier to do it in other ways. However, Kevin Titus, could you explain the second step? I get the bit of making it a unit vector, but what's the bit of it having a magnitude of 1? Could you explain? Get the bit of making it a unit vector, what's the bit of it having a magnitude of 1? Oh, well, that is the bit of having it. Wait, I don't fully understand. Could you just explain your question a bit better on the...
Hello,
Yeah, I can
are
hear
you
you. Yeah,
hearing?
what's up?
No, it was my misunderstanding. I was like, oh, you know where you wrote where the magnitude of v equals 1. What does that mean? But then I realized
Oh, that's what we're just
that,
trying to make it do. That's what a unit... I'm saying that's what it means to be a unit vector.
yeah, that's fair. I get you.
All right, cool. No
Right.
worries. Cool. What a lovely guy. Right, so now we move on to an actual practical 3D question. So this is something you could actually get, or an actual problem that a gradient descent algorithm could face, because it makes a lot more sense to have this in 3D. With 2D, there are other ways to do it, which are much simpler than working out a directional derivative. However, in 3D, it makes a lot of sense. When you want to go in a certain direction, you calculate the gradient in that direction. Let's say we have a function f of x, y, and z, and this is the function, x squared plus y squared minus z squared. Normally, in a gradient descent, x would be some independent variable that we're, working out, and y would be another independent variable, and z would be the cost function, which we want to minimize. So, which represents the concave surface in a 3D space. Find the directional derivative of f of x, y, z at the point p123 in the direction vector v221.
So we have the same stuff, but we're just applying it in 3D now. And I'm taking this is the entire question that we could get in our exam, and we'd need to go through all the steps to work out the directional derivative. So this bit definitely, I want someone to take the lead on this problem. I want someone to have a go. Basically, you don't need to be correct and all of that, but yeah, I'm gonna do it right now live, but I want someone to guide me through it, kind of like um, to show if you've learned it properly. So,
Does anyone want to volunteer? Can you give us 2 to 3 minutes to work through it? Yeah, absolutely. Yeah, yeah, I'll give you some time. This is
yeah, a very lengthy process to work out all of it. So yeah, take your time. Tell me in the chat when you have worked out an answer, and yeah, I will
get you onto the stage. So I just had a question about explaining what v hat was. So if you look back at the this slide, so v hat here is all it is essentially is just the unit vector of v. So the hat on top of a vector is, the lecture is recording. Thanks for reminding me. So the hat on top of the v is one. It's basically just the unit vector form of the v. It's just the notation, and Are you familiar, Victor, with what a unit vector is? Okay, so a unit vector is basically a vector with magnitude 1, right? So what is the magnitude of the vector that I initially gave you? What's the magnitude of 1, 1? Square root of 2, exactly, we worked it out here. So the magnitude of this vector is square root of 2, and you do that by taking the horizontal component and the vertical component and using Pythagoras to work out the hypotenuse. That gives us the magnitude. But we don't want a magnitude of root 2 because that would kind of skew our dot product. We only want just the raw direction. We don't want any magnitude to skew that up. And the way we do that is by making the magnitude 1 while maintaining the same direction that we had before. And the way we can do that is by dividing both the horizontal and the vertical component by the same factor. So here we have a magnitude of root 2. So the way we can make sure the magnitude is now 1 is by just dividing the horizontal and the vertical component by root 2. Hence, v hat is 1 over root 2 and 1 over root 2 because 1, 1, we've divided both of them by root 2. So if you were to now work out the magnitude of 1 over root 2, 1 over root 2, what do you get? Can you work it out using the Pythagoras that you did to work out root 2? Can you work out the magnitude of the unit vector 1 over root 2, 1 over root 2? Exactly, it's 1. So all we did there was we just made the magnitude from root 2, we just made it 1. And the process was by dividing it by the magnitude so that the magnitude became 1. That's the process of making any vector into a unit vector. Do you now understand two things? Do you understand why we need a unit vector, and do you understand what v hat is, aka the answer to your original question? I get it, yeah. Okay, cool. Cool. No worries, no worries. Shay's put the problem there. Nice, nice representation. Good. How's everyone doing with the problem, by the way? Any volunteers? All right, so we've decided to just go through it together. I can see this is quite a tricky question, right? But I can't see the question anymore, actually. I can't see the question. Okay, I'm going to plug in my drawing board real quick and we'll go through it together. Okay, right. So, right, let's go through this. We have, yes, we have the mouse. All right, cool. So we are using x squared plus y squared minus z squared as, and then we're also finding it for 1, 2, 3 in direction 2, 2, 1. Right, okay. So, can anyone say, I don't need you to explain the entire thing, just the start. So how are we going to start, basically? What did we do last time? Can anyone remember? Calculate the gradient vector. Yep, that is what we're trying to do. Partial differentiation. There we go, Kevin. Correct. So partial differentiation, we write it as delta f. I should have probably mentioned that this is f of x, y, z. Okay, right. Delta f over delta x. So let's work out the partial derivative of f with respect to x first. So can anyone tell me what what's the partial derivative that they got for this delta f over delta x? So a reminder is that this is where we only treat x as the variable and everything else is a constant. So what is the um, partial derivative here? Anyone got it? Kevin, perhaps? Oh, you got the whole thing. Yep, cool. So, yep, correct. So this is 2x, and then it'll be plus 0 because the other ones would be constants, and then delta f over delta y would be 0 plus 2y plus 0, and then delta f over delta z would be, correct, minus 0 plus 0 minus 2z. I hope everyone's happy with how we've got that. So, yep, that's cool. So now that we have this, we can say that the gradient that we want to work with is 2x, 2y, and minus 2z. You happy with this? I mean, Kevin's clearly happy with it, so that's good. Right. So, what do we do from here now? So we have this. What was the next step? So, does anyone remember what the next step was? Why am I not able to scroll? Okay, scrolling down a bit. Well, we can do that next, but it's not what we did next. Sub in, yep, exactly. Sub in the points. Yep, exactly. Good job, guys. So, the point we were working with was 1, 2, 3. So we have for 1, 2, 3, we sub in 2 times 1, and for the next one we have 2, 2, and for the last one we have minus 2, 3, which gives us the gradient vector, sorry, not the gradient vector, the gradient at point 1, 2, 3 r's, 2, 4, and minus 6. All right, everyone happy with how we got up till here now? I'm assuming, yeah, okay, cool. All right. Now we have to do what Shay said earlier. We have to unitize the vector. So we had v as equal to, if you look up, 2, 2, 1. So how can we turn 2, 2, 1 into v hat? What would v hat be? There we go. Shay's come up with the solution there. So, yep. The square root of 2 squared plus 2 squared plus 1 squared gives us 3. That's quite nice. However, we don't want it to be 3. We want it to be 1. So we divide every axis on this vector by 3 to get a unit vector. So 2, 2 third, 2 third, 1 third. All right, everyone happy with this unit vector now? Cool. All right. Let's now move on to the last step. Now, just to calculate the directional derivative at this point in this direction, we need to do what? Dot, yeah. Dot is correct. Dot product, correct. Okay, so we have what we had before, which was okay, so previous bit was 2, 4, and minus 6. So we dot product 2, 4, and minus 6 with our unit vector, 2 third, 2 third, 1 third. Has anyone done this on their calculator? Is 12 minus 6 is 6 over 3, which is equal to 2. All right. Yep, so Shay's put that down there.
Cool. So This is our final answer. This is gradient vector for, I see what you mean there. It's okay, yeah. It's more like calling it the gradient. I feel like the better way to describe it is using the word directional derivative. Yeah. Yeah, directional derivative. Gradient vector is kind of what you'd use when you say the derivative combined with the vector that we're working it out for. That's like the gradient vector. So that is in fact what gradient descent algorithms would use. They use gradient vector.
Yeah, yeah, exactly. So you're just multiplying it by, yeah. Cool. And that's the directional derivative for the function at this point in this direction. Does anyone have any questions or would like to run through another example? How are we feeling about this? Is everyone confident? Got it? Shay's got it. If you think you've got it, can you react to Shay's message? Um, get it better now? Okay, cool. That's good. That's what the point of this session was. Good to know that people are understanding it better. Okay, does anyone, and it's going to take a lot of bravery to speak out about it, so does anyone not understand it? Does anyone not get like something we've done or how we've got to this answer? Don't worry, there's only 10 of us in the call, so I think it's in your best interest to speak out now if you don't get it. No? Okay. All right, cool. So yeah, that's pretty much the lesson. That's differentiation, directional derivatives, gradient vectors, and multivariable calculus for you. All right, thanks guys for joining. I hope you guys found the lesson useful. Yeah, no worries. No worries. Cheers, guys. I'm gonna end the recording now, and I'll be in the VC to chat or answer any questions if anyone has it. So, yep. Thanks, guys.